Hi everyone. So from this session onwards, we'll start our module 2, that is antenna parameters. So some key highlights again I have mentioned here, that is obviously we'll look for different kind of parameters for how to analyze your antenna. Then further Smith chart and quality factor also will like to discuss in this module. Okay. So basically, what are antenna parameters? Basically, I'll say that whether it is one kind of performance parameter as well as physical parameters by which your performance parameters can be altered. Okay, so antenna parameters by which you can say your antenna is achieving so and so value so that it is acceptable and at resonate and resonating in so and so frequency so that it is applicable for that particular application. So based on that application, what should be the minimum gain, what should be the minimum return loss, like that. So these are the terms by which your antenna can be analyzed. Okay, so first of all, in order to measure this antenna parameters like gain, directivity, S11, or you can say the return loss, VSWR, directivity, at what distance it has to be measured. So basically, these these parameters are measured in the far field distance. Okay, so this far field is also some two types I can say, near field and far field simply. Far field means Fraunhofer region, near field means Fresnel region. Okay, and that too radiative near field is called a Fresnel region. Okay, so in the right side, if you can see that that pink color triangle is nothing but a antenna only. Okay, and then further, what will be the distance? What will be the distance if its dimension is linear dimension is d, capital D? So reactive near field will be having a distance of 0.62 under root d cube by lambda, where d is the linear dimension of the antenna, lambda is the wavelength of at that particular frequency. Okay, then now in coming to radiative near field, now radiative near field is having a formula of less than 2d square by lambda, and whereas the far field obviously it will be having a greater than 2d square by lambda. Okay, regarding this far field, this wireless communication, generally these parameters will be measured in this far field region, but in case of EMIMC, lightning effect, okay, so, such applications are measured in near field region. Okay, now this in the case of reactive and radiative fields, these fields, whatever the fields are propagating, so that is not orthogonal. Okay, so that's why it is not predetermined that whether these fields are dominating or not. So that's why we are not able to measure the parameters at such distance. Okay, because some distance will be at some distance it will fields may get deteriorated and any okay, so that place in that place far field region is the distance by which we can measure. Now, these antennas, when this radiation occurs, means the emitting of the field will occur, then it will form some pattern from the antennas. So these patterns are also having some shape, and some types of patterns are also there, which is nothing but isotropic, omnidirectional, and directional, called as. Okay, so this isotropic is kind of, I'll say that is kind of a theoretical antenna, because I'll discuss it why it is a theoretical antenna and not as a practical antenna. Uh, okay, and then further it is further it is having a omnidirectional antenna, can also give a omnidirectional pattern, and then directional pattern means your radiated power is, most of the radiated power is consist in the main beam. Okay, so this antenna pattern or a radiation pattern can be plotted in a 3D graph as well. 3D gain, 3D directory, I guess you might have heard. This pattern is measured in volt per meter, okay, versus degrees, okay. And further, this antenna pattern will also depicts the field strength of your antenna, okay. So again, regarding this theoretical of omnidirectional directional, I'll say that so omnidirectional is the pattern, kind of a pattern which gives by dipole antenna or monopole antenna or any other pattern which is having a omnidirectional. Then omnidirectional pattern in which the radiation occurs in only one plane, either in E plane or in H plane. Okay, so regarding the isotropic regarding the isotropic, I'll say that equal radiation in all the direction. Okay, so that's why the image was of iso means a full sphere means full equal direction equally in all the directions. Okay, then directional means whatever I have told you that the maximum radiated power is consist in the main beam. Okay, so that is nothing but a highly directional we can say, and this can be achieved with the large array antenna also, because it is having a number of elements and in collective way it will be easier in order to achieve that pattern. Okay, now antenna beam width, I'll say. Okay, now antenna beam width is in the generally it is having a omnidirectional directional only, because it is lies in a omnidirectional directional only because as I said, this isotropic antenna is kind of a theoretical antenna. It does do not exist in the real life. Okay, so whenever this antenna radiates, so it will depict the angular separation between the left and right side of the radiation pattern, and it the unit of this beam width will be in dB. And then angular separation, or you can say the second definition of this antenna beam width will be angular separation between two 3 dB half power point. Okay, and two types are there for the beam width, that is first null beam width and half power beam width. First null beam width is related to the half power beam width by 2.25 multiplied by half power point. Generally, what will textbook will do that they will do take as a roughly as two times only. But for a more specific way, it is 2.25. Okay. On one image, I would like to show that this is one kind of a directional pattern only, directional radiation pattern. So as you can see in this left and right, it is having a half power point right, half power point left. And further, the main lobe, which is having a full, or you can say the maximum amount of radiation power during in the maximum direction. Okay, and the first null beam width will be denoted in a lower region, and then in case of minor lobes, these are also minor lobes, or you can say the side lobe levels, which are totally unwanted, because these are the also kind of a lobe which will consist the, as you can say that radiation power only, but it is not able to detect during the receiver side because of the very small amount of power. So that's why during this transmission, so this will get deteriorated because of the noise interference or the distortion. And anyway, even though it is very so much in number, but then also it is not able to detect by the receiver. Okay, then we come to the polarization, which is nothing but the orientation of the electric field. Polarization types is also there, which is linear, elliptical, and circular. Okay, so linear, elliptical, circular. And how this, in case of RSCP or LSCP, that is left hand circular polarization or right hand circular polarization, that E field will, or you can say the E vector will rotate. In LHCP, the radiation, or sorry, the field vector will rotate in a clockwise manner in the case of LHCP. But in the RHCP, the field clockwise will rotate in the anti-clockwise. Okay, then further, I'll say that during suppose in case of CST and all, this just for depiction purpose, I am saying how the field vector we can say. But in the case of CST, with the help of axial ratio AR, we can depict our polarization. Okay, generally if it is having a nearly to 1 dB, then it is LHCP, and in case of it is having a greater than 3 dB, then it is known as for linear polarization. Up to 3 dB we are saying that it is having a circular polarization. Then coming on to some more parameters, performance parameter, which are crucial for your antenna. Those are directivity, gain, and efficiency. Okay. Now, first of all, these formula which I have mentioned here, it is taken from Balanis book only, so you can also refer that. Okay. We'll continue this performance parameter in the next lecture.